Hello everyone, this is Mr. Keppel. This is PHYZR number 7, the law of inertia. This is from the force unit, it's page number 2. Today's PHYZR will be discussing inertia and Newton's first law of motion. We'll do a quick little run-through breakdown of what Newton's first law is, and then we'll be applying our understanding of Newton's first law to solve a very interesting question. Let's get started. Simply put, inertia is the tendency for things to remain unchanged. This is Newton's first law of motion. So inertia means that things want to stay the way they are. Things have this tendency to remain unchanged. And this is the concept of inertia. You've probably heard this expressed as an object in motion tends to stay in motion, or an object at rest tends to stay at rest. That's the concept of inertia. Inertia is what keeps things the way they are. It's this natural tendency for things in the universe to either stay at rest or to move at constant speed in a straight line path. So an object at rest stays at rest. This is a picture of balanced rock at Arches National Park in Utah. And balanced rock will stay balanced and it will stay at rest unless there's an unbalanced force applied on the rock. This is what Newton's first law of motion says. It says that when forces are balanced, no acceleration occurs. But when forces are unbalanced, then an object will accelerate. So an object at rest tends to stay at rest unless there's an unbalanced force that acts on the object. The same is true for an object at constant velocity. An object at constant velocity stays at constant velocity unless there's an unbalanced force. Realize that rest and constant velocity, uniform motion in a straight line, are equivalent as far as the forces are concerned. Both objects, rest or constant velocity, have the same amount of total force on them, which is 0. The forces are balanced. So this is the law of inertia. The law of inertia essentially says force is not required to keep an object in motion. That objects naturally stay in motion. You don't have to keep pushing an object to keep it staying in motion. So objects will naturally stay at constant velocity or stay at rest. This is the law of inertia, that inertia tends to keep things unchanged. Now you might say this doesn't seem right, because I know that if I'm driving a car and I take my foot off the gas pedal, that the car will slow down and eventually stop. Or if you're pedaling a bicycle, if you stop pedaling, the bike slows down and stops. So that doesn't make any sense, because if I want to keep the car going forward, I have to keep pushing the gas pedal and applying a force to keep my car moving. But realize that what you're actually doing is when you're stepping on the gas or when you're pedaling a bike, you're actually applying a force that balances the force of air resistance and friction pushing back on the car. So when you pedal a bike, you are keeping the forces on the bike balanced. So there's no net force. As long as your bike is moving at constant speed in a straight line, there's no net force. The forces are balanced. And when forces are balanced, the object stays in motion. So if forces aren't required to keep objects moving, then what do forces do? What exactly does applying a force on an object do to the object if it doesn't make it move? If two objects move at uniform motion, if we apply a force on the top object, it accelerates, but the bottom object keeps moving. This is what forces do. Unbalanced forces cause acceleration. They change the velocity of an object. So it's not that a force keeps you going, but it's that a force changes your velocity. If you apply a force on an object, it will either speed up, slow down, or change direction. This is the law of inertia, that balanced forces have no acceleration. When an object has a balanced force on it, it does not accelerate. That acceleration can only occur from unbalanced forces acting on an object. So here's a demonstration we're going to do. So suppose that a mass is suspended from a support by a string, just like shown in this picture. There are two strings. There's a string on top that the mass is hanging from, and there's a string on the bottom. I want you to draw this picture in your notes. And the question we're asking is, what will happen if we pull the bottom string? I'm going to pull this string as hard as I can, as quickly as I can, and as hard as I can with all of my strength. I'm going to pull down on the bottom string. And I want to know what's going to happen. So obviously there are two possibilities for what will happen when we pull the lower string. Either the top string breaks or the bottom string breaks. One of these two outcomes must occur. And the question is, which one is it? Is the top string going to break or is the bottom string going to break? Now before we decide, we should probably think about this in a little bit more detail, just to make sure that we're not just guessing. We want to really understand and try to predict what will happen. The first question we need to think about is, why does a string break when it's pulled? So what even causes a string to break in the first place? Why can't a string just stretch out forever when it's pulled? Why does a string break? The idea is that when you pull a string, it causes tension. And so it's tension that breaks the string. As you stretch the string further and further, the tension increases linearly until the string snaps. If you don't know, tension is a force due to the stretching of a string or rope. So it's the physical act of stretching that causes the string to break. If the string didn't stretch, then it wouldn't be able to break. So what happens is, stretching the string reaches this point where it can't stretch any further. The actual thread within the string can't hold that force, and so the string snaps. So let's apply this idea of tension to say which string is under a higher tension in our apparatus. Which string, the top string or the bottom string? Right now, as this is set up, which string is under the greater tension? If we can figure out which string has a higher tension, then logically that would be the string that breaks. The string with more tension is going to break. And we know the top string has more tension than the bottom string, since the top string is pulled down by the weight. So this weight is being pulled down by the gravitational attraction to Earth, and it's stretching the top string. The bottom string is not being pulled down, so the bottom string has no tension, and the top string has lots of tension. By this reasoning, we would say that the top string should break, since pulling the bottom string down will also pull the mass down, which will then pull the top string even more. While tension is added to the bottom string, an equal amount of tension is added to the top string. And since the top string already had more tension, then the top string is the one that should break. Okay, so we think that the top string will break. Well, what about this? Which string do you think would break if someone held the mass in place? Now, I'm not actually going to hold the mass in place, but it's just curious to think that if someone grabbed hold of this mass and firmly fixed it in that location and didn't allow it to move, then which string do you think would break? So if the mass were held in place, then the bottom string would break, because the top string wouldn't be able to stretch. So if you fix that mass's location by firmly holding it in place, the top string would not be able to stretch because the mass wasn't able to move. So the idea is that pulling the bottom string moves the mass, which then stretches the top string. If we held the mass in place and didn't allow it to move, the top string wouldn't stretch. So the only possibility would be for the bottom string to break. It's time to make your decision. Which string will break? I'd like you to write down on your page just a quick little explanation of which string you think is going to break. Remember the choices. We're going to pull down on the bottom string. Do you think the top or the bottom string is going to break? And I want you to justify your answer and make your case. Now I hope you've actually written something down, because if you haven't, you're about to learn nothing. So please make sure that you have something written down on your paper. If you haven't, go ahead and pause this video and write something down. It's very important that you commit to making your prediction before we reveal what happens. Okay, so this is going to be our first attempt. We're going to do it twice, of course. So this is the first attempt. Remember, I said I'm going to pull as hard and as fast as I possibly can. Here we go. Okay, so when the string was pulled quickly, the bottom string broke. Why did that happen? So the idea is that because the string was pulled so quickly, the mass didn't move. Its inertia held it in place, so that force didn't have enough time to act to accelerate the mass. Since the force was applied in such a brief amount of time, the mass pretty much stayed in the same place. So the top string wasn't able to stretch, and the bottom string broke. It was just as if someone were holding that mass in place, except it wasn't a person holding it, it wasn't a hand, it was inertia that was holding it in place. Okay, let's try it again. So this time I pulled the string slowly, but I still pulled it as hard as I could. I just pulled it slower. And now the top string broke. Why did that happen? This time the mass did have a chance to accelerate. When the string was pulled slowly, the mass was moved, that this unbalanced force was able to accelerate the mass, which then caused the top string to stretch. Since the top string already had more tension, obviously the top string breaks. Here's something else to consider. What if instead of using a weight like this mass, what if we used a ping pong ball? Would this demonstration work better? Meaning, would I still be able to break the bottom string? What do you think? If we had a ping pong ball, do you think I'd still be able to break that bottom string? We have to realize the only reason the bottom string was able to break was because the mass couldn't move, didn't have a chance to move. And a ping pong ball is really light. It's extremely easy to accelerate a ping pong ball. It would be extraordinarily difficult to get the bottom string to break with the ping pong ball. So this would not work better. Since the ping pong ball is really easy to move, it has very little inertia. And that's going to be very difficult to get the ping pong ball to stay in place. I would have to pull it extremely fast. I probably wouldn't be able to pull it fast enough. And so what we realized from this is that inertia is a property of mass. That an object with more mass has more inertia, and an object with less mass has less inertia. So it's easier to change the motion of objects that have light mass than it is to change the motion of objects with a large mass. So for example, if you were going to try to push a train, a freight train, it would be very difficult to push that train. It would take an extreme amount of effort on your part to change the motion of the train. But if you think about a roller skate, it's pretty easy to change the motion of a roller skate because a roller skate doesn't have nearly as much inertia as a train does. We'll be talking about this idea of inertia later on in class when we discuss Newton's second law. But for now, just realize that inertia is a property of mass. The more mass something has, the more inertia it has, the more it wants to resist a change in its motion. One final thing to think about is how gravity fits into all this. So what if we did this experiment in the absence of gravity? Could we still break the bottom string? This question is very important because inertia doesn't depend on gravity. We would totally still be able to break the bottom string. Inertia and gravity are completely separate concepts. So the difference is if we did this demonstration in the absence of gravity, there wouldn't be any weight pulling the mass down. But the mass would still be equally difficult to accelerate. It would still have the same amount of inertia. And so if I yank that bottom string as hard and as quickly as I can, the bottom string will still break, and the mass would stay in the same place. Or it would accelerate very, very slightly. It would barely move at all, but the top string would keep it attached to the support. Well, that's it for this PHYZR. I hope you guys have a wonderful day. This has been Mr. Keppel, and I'll see you in class.